So section 10.2 is going to discuss parametric equations. And I remember when I first saw parametric equations, they talked about a parameter. And I looked up the definition of parameter in the dictionary. And it said something that varies. And I'm like, wow, I think my reaction was something like welcome to Facebook or something like that. I wasn't really happy with it. In any case, it is something that's going to vary. Parametric equations are equations that depend, you have an x and y that depend on something else, and that something else is your parameter. And that's what is going to vary. Thank you very much, Merriam-Webster. So let's do this. Let's plug in a couple of values for t and let it vary and see what happens when we do that. See what we get for x and for y. So let's start out with a very simple t equals 0. Now if t equals 0, I'm hoping we don't need something fancy like a graphing calculator to figure out what x is. If t is 0, then x is 5 and y is 2. And that really gives you a coordinate pair of 5 and 2. Okay, let's try some other values, like t equals 1. If t equals 1, again, you're going to get some more x and y values. If t is 1, x is 1, and y is 7. 1 and 7. And we'll do one more by hand, and then kind of call it a day on that part of things. If t is 2, then we get negative 3 for x and positive 12 for y. Negative 3 and 12. Now, of course, you can put in other values of t in between all these and above, below, either 0 or 2. But what's going to happen is that it's eventually going to trace out a line. And you can kind of see the trend here. Every time I increase t by 1, I'm decreasing x by 4, and I'm increasing y by 5. So it's going to go up in a nice systematic pattern. But let's try and figure out what that line is going to look like. And we can do that if we eliminate the t here, eliminate the parameter. So how do I do that? Well, I can solve for t from one equation and then substitute the expression into the other equation. So let's see. Let's do that from here. Y minus 2 equals 5t. Y minus 2 over 5 is equal to t. If I take that and I take this expression and plug it in here, now I'll have an equation that just strictly depends on x and y. So let's see what that gives us. X equals 5 minus 4 times y minus 2 over 5. If I distribute here, I get x equals 5 minus 4/5 y plus 8 over 5. When I combine like terms here and here, let's see, we'll regard this as being 25 over 5. So it'll be x equals 33 over 5 minus 4 over 5 y. Not exactly a really pretty equation. We can maybe clean it up a little bit more. If I multiply everything through by 5, I get 5x equals 33 minus 4y. Or better yet, moving this to the other side, 5x plus 4y equals 33. And that's not too bad. That's something you can graph pretty easily, either on your graphing calculator or something like Desmos. Nice. Let's actually do this on our graphing calculator and learn a little bit more about these kinds of things. So the first thing we're going to need to do is go to the mode key. You need to change the way we work with our functions. Instead of working with function, we're going to work with parametric functions. So cursor down along the left side, go over to parametric equations, and then press enter. Now when we make that change, when you press the y equals key, you should see something different. What's different about the setup here at y equals? You've got an x and a y. So you need a pair of these for each equation that you're going to graph. Let's enter in the equation for problem number 2. That was 5 minus 4t. Now you might ask, where do you get the t? Well, you get the t when you press the x's. Notice that this button is x, t, theta, or n. It depends on if you're in the regular function mode, parametric mode, polar mode, or sequential mode. So depending on what mode you're in, you're going to get that variable when you type in that key. 2 plus 5t is our other equation. Okay. Now we have to set up our window. Setting up the window is a little bit different here because in addition to x-min and x-max, you also have t. And you have to tell where you're going to see t. Let's just start out very modestly of t between 0 and 2. And a step of, say, 0.05 should be pretty good. The rest of this, you might want to let your calculator handle. So, does anyone remember how to do that? To make your calculator figure out what the window should be. Zoom 0. So zoom and then 0 gives you zoom fit. So, nice. But I guess what it doesn't show you is really what's going on in a sense. And that is, when you graph this, if I zoomed out a little bit, when you graph this, you're only getting a little piece of that line. If I want more of that line, then I'm going to need to vary t in a wider range. So I changed my window. If you wanted to kind of follow along, here's my new window. Negative 15 to 17 on the x-axis, negative 13 to 27 on the y-axis. But let's actually add something to t. Let's go from 0 to 5 and see what that does for my graph. So I get a little bit more of the graph. What if I started at maybe negative 4? I get even more now. So eventually, if you let t take on, a whole range of variables, you can get the same thing that you would get if you graphed the equation 5x plus 4y equals 33. Now let me do one last thing here. I'm going to go over here and do something we did last week, and that is I'm going to change the style of the line here. You want the one that looks like a little circle with an appendage sticking out here. Perhaps an unfortunate choice on the part of TI, but whatever. Let's click that one. And what I want you to notice is the direction in which this gets traced out. So we're okay there. When I hit graph key, notice it starts out in the lower right and it moves towards the upper left. That's what's called its orientation. So depending on your choice of parameters, you're going to give the graph an orientation. I'm not trying to draw this anywhere near exact, although I think I will take at least a little bit of time to plot the y-intercept. Would be 33 over 4, so 0 and 33 over 4, and the x-intercept would be 33 over 5 and 0, so something like that. But the orientation is the way that this curve is traced out. So as t increases, it gets traced out in this direction. Like I said, that's its orientation. Now, I could come up with different parameterizations of this line that would have different orientations. It would trace it out in a different direction. That's okay. This one's fine for kind of a beginning example. Are we okay with this? And what you should get is a couple things. Some of the things we're going to do is, or are, eliminate the parameter from your equations to get an equation in x and y. We did that here. We ended up with this equation. We also graphed it to determine the orientation. So those are a couple of things you should have gotten from this example. Now, the tricks you're going to need to eliminate the parameter are going to change from one problem to the next. So before I move on to problem number 8, are we okay with problem number 2? All right, thanks, Ronnie. Let's take a look at problem number 8. X equals t squared plus t. Y equals t squared minus t. We can graph this, take a quick look at things. So let's put it into our graphing calculator. I'm going to change my equations here. I need t squared plus t and t squared minus t. Okay, not bad. And I'm just going to run with my current window, even though it's probably not ideal for this. Let's just see what happens. So it's something like that. Kind of looks like a sideways parabola. Tough to say. I can kind of zoom in a little bit. The zoom box feature is actually pretty cool. You do zoom box, then you move over with the cursor until you find one corner of what you want to be your new viewing window. Press enter and drag out a box that you want to be your new viewing window. And let me just tighten that up a little bit. There's my new viewing window. And you can see a feature that you couldn't quite see before, and that is this graph tucks a little bit to the left of the y-axis and then dips underneath the x-axis. Okay. Here's that viewing window if you wanted to try and get something similar. All right. Let's take a look at eliminating the parameter here. Now, we've got a t squared and a t here. It's going to be kind of challenging to get rid of both of these. But we're going to have to do that somehow or another. And one thing that occurs to me is that if I subtracted y, or let's multiply everything by -1, I get this here. If I now add this and this, at least my t squareds are going to cancel each other out. That is x plus -y, adding these together gives me t squared plus t minus t squared plus t. So I almost got rid of my parameters. Minus x minus y equals 2t. But at least I can now get an expression for t. X minus y over 2 is equal to t. Okay. X minus y over 2 is equal to t. Now that doesn't quite get rid of it. It just solves for it. But to get rid of it, I need to plug that expression back in one of these equations. And I can plug it into either one. I'll get an equivalent expression. If I plug it in here for the equation with x, I get x equals x minus y over 2 squared plus x minus y over 2. I don't think you're really going to be able to make that expression a whole lot prettier. It's just going to be kind of an ugly expression no matter what you're stuck with. If you substitute in for y, in here you would get y equals x minus y over 2 squared plus, actually minus minus in this case, minus x minus y over 2, like that. Okay. Let's see if the graph of one of these matches what we have on our graphing calculator. And I'll do that on Desmos. So there's one. Looks pretty good. If I shut that off, the other one is identical. So getting the same thing either way, which is good. One last thing that we should do for this is plot the orientation. So let's take a more careful look at this, how it gets graphed out. So I'll go back here, and well, I do have it set up like that. I'll just adjust the window a little bit. Let's go t equals, say, -5 this time. And I'll hit the graph key, and it comes in this direction, goes out that direction. So that's its orientation, is the direction in which it was traced out. So the orientation is like this. Okay. Looking all right for these first two. Are you all right with graphing these things on your graphing calculator? And finding the orientation? All right, those are a couple things that we'll do. We're not done here, but next week we'll work in finding the rate of change, that is the slope, the derivative of these types of things. It's going to be a little bit reminiscent of what we did to find the derivative in the case of polar coordinates. But take a look at problem number 18. X equals 3 cosine of theta, and y equals 7 times the sine of theta. Start out by trying to graph this. Now, they've got a theta there. You can use t when you plug it into your graphing calculator. You're going to have to come up with some values to vary theta over. Now, if you're working with sine and cosine, what would be some good values or good range for theta? From what to what? Yeah, 0 to 2 pi. Because you know that sine and cosine are periodic with that period. Now take a look at the graph that you get, and maybe you'll understand a little bit about why we did section 10.1 tonight as opposed to following the syllabus, because you should see something that looks a little bit familiar. Okay, so should be putting in equations like this. Then we can adjust our window. T min to T max. We'll go from here to 2 pi. And then I'll let my calculator do the rest. So it's going to be zoom and then the 0 button. And it's thinking, it's thinking, it's thinking, and then finally it'll give me the graph. What's the graph look like? An ellipse. So, wow, cool. It's an ellipse somehow. You can hit zoom 5 to kind of square that up and get a little better look at your ellipse. It's actually taller than it is wide. The previous graph is a little bit misleading, wasn't it? So it's not a bad idea if you keep in mind zoom square. Zoom square is going to adjust your axes so that when you graph a circle, it'll actually look like a circle instead of an ellipse. Question is, how do I show that it's that equation? How do I get rid of the parameters here? The parameter is theta. The trick is this, and this is a good one, so make sure you catch on to it. I'm going to divide both sides here by 3 and both sides over here by 7. And that doesn't look like I've done much. Don't get embroiled in trying to solve for things with an inverse cosine or an inverse sine. Trick here is quite simple. I'm going to square both sides. X over 3 squared equals cosine squared of theta. Y over 7 squared equals sine squared of theta. I still haven't gotten rid of my parameter, but I'm one step away from it. If I add these two together, that is x over 3 squared plus y over 7 squared. So I add the left-hand sides. That means I also have to add the right-hand sides, right? So cosine squared of theta plus sine squared of theta. What was the genius in what we did here? Yeah, this is equal to 1. Cool, right? Because of the Pythagorean theorem. So overall, you get something which you recognize as the equation of an ellipse, x over 3 squared plus y over 7 squared. I don't need a double square there, sorry. Equals 1. Nice. And that matches what we saw when we graphed this thing. Let's try another one similar to that. Are we okay with this one? In the same way we did the last one, you could do this one. You can find the orientation. If I go back here, I mean, my trick sometimes is just to adjust the window minutely to make the graph draw again. So I'll do 6.3 as Tmax. And the orientation starts out at the positive x-axis and goes counterclockwise. So that would be the orientation. Nice trick there on problem number 18. We're going to use a similar one for problem number 22. X equals -2 plus 3 cosine of theta. Y equals -5 plus 3 sine of theta. Kind of like the last one, maybe you want to start out by graphing it. What does the graph look like? Okay, let's do that. Let's enter in each of these equations and see what the graph looks like. So we'll do x is -2 plus 3 cosine of theta, or in our case t, and then y is -5 plus 3 sine of theta, and again, in our case t. As far as coming up with a graph is concerned, we've already got our window set from 0 to 2 pi. So I think it's probably a good idea to leave it there. If we hit zoom fit, that is zoom and then 0, it helps give you a decent looking graph, but it's a little bit misleading again. Our equations are not an ellipse. If you hit zoom 5, you might get a better look at what their equation actually is here in this case. What do these equations represent? A circle. All right. So squaring things up like that gives you a circle. See if you can't take a minute and try and find the equations of that circle. Use the trick that we had in problem number 18. All right, looking pretty good. Let's start by trying to solve for the cosines and the sines. I'll move the 2 to the other side, so I get x plus 2 equals 3 cosine of theta. And then getting the cosine by itself, x plus 2 divided by 3 equals cosine of theta. And finally, we'll square that. X plus 2 over 3 squared equals cosine squared of theta. In the same way, we'll get y plus 5 divided by 3 equals sine of theta. So y plus 5 over 3 squared equals sine squared of theta. If I add those together, I get x plus 2 over 3 squared plus y plus 5 again over 3 whole quantity squared equals 1. Now, why is this a circle? Well, if you notice, I've really got x plus 2 squared over 9 plus y plus 5 squared over 9 again equals 1. When I multiply both sides by 9, I get x plus 2 squared plus y plus 5 squared equals 9. That's a circle with a center at -2 and -5 and a radius of 3. That's exactly what we have graphed right here. Kind of a neat parametric equation. I'm not really going to spend much time on it. It's something called a cycloid. So let me just kind of give you a real basic one here. 2 times t minus sine of t, and then in the below equation I'll do 2 and then 1 minus cosine of t. T. Window, zoom fit. It's going to be a little bit stretched, that's all right. Let's actually extend this a little ways longer. Times 4, and then enter, zoom 0 again. So what a cycloid is what the graph would be like if you looked at a point on a wheel as it's moving forward. How would that point move? And you should see a sequence of ups and downs, bouncing off, and coming back up again. So that'd be the path of a point on a rim. Let's do one more, kind of like the previous couple, and then we'll work on some things backwards. Problem number 24, similar to what we've seen in some of the last two problems. So we've got x equals secant of theta and y equals tangent of theta. Did you want to graph that and take a look at what it's going to look like? All right, not many takers, that's fine. Nonetheless, if you're trying to eliminate the parameter here, then what are you going to do? I mean, we can play our same game. We can square it. X squared equals secant squared of theta. Y squared equals tangent squared of theta. But then what? How do we get rid of theta? Perfect. Now, if you can't quite remember that, let's look back at sine squared of theta plus cosine squared of theta equals 1. And in thinking about this relationship, if you're to write this in terms of sines and cosines, what's going to be in the denominator of both of these? Cosine squared. So let's divide everything through by cosine squared of theta. Cosine squared of theta, cosine squared of theta. And now we can simplify this. That's going to be tangent squared of theta plus 1 equals secant squared of theta. Or, another way around this is if I move this to the right-hand side, I'll get 1 equals secant squared of theta minus tangent squared of theta. There's a lot of different forms of the Pythagorean theorem, and it's tough to keep them all memorized. But if you're comfortable manipulating it, you can come up with whatever you need whenever you need it. So in this particular case, if I want to do secant squared minus tangent squared, then it's going to be x squared minus y squared is secant squared minus tangent squared equals 1. What kind of graph is this one? If you were to graph it. Yeah, hyperbola. Yes, well done. Okay, a couple more problems. We're going to start out with the equation of a line and try and find, or actually not start out with the equation of a line, start out with a couple points on a line and try and work backwards to find a parametric version of that line. So I want a line through these 2 points, 1, 4 and 5, negative 2. Let's start out by just finding a regular old line in x and y. So this is basically an algebra problem at this point. We'll get the slope. So negative 2 minus 4 over 5 minus 1 gives me negative 6 over 4, which is negative 3/2. Nothing too exciting here. We'll just plug that in to this formula. Y minus y1 equals m times x minus x1. Choose your favorite point for x1, y1. Since these are both positive, that looks like an easy choice. Y minus 4 equals negative 3/2 times x minus 1. So it's negative 3/2 x plus 3/2. Now I'm going to add 4 to both sides to get rid of that 4 here. But on the right-hand side, instead of 4, I'll write it as 8 over 2. So I get y equals negative 3/2 x plus 11/2. Well, that's an equation in x and y. What's nice about this is that I have it solved for y. And that's going to make it really easy to come up with some expressions for x and y as a function of t. There's kind of like your basic one. If you let x equal t, well, if I put in a t here, then y would be negative 3t over 2 plus 11/2. So that's an equivalent parametric version of that equation. And in fact, anything you want to drop in for t will work. You can do something a little bit more off the wall, like x equals e to the t. And if I plug in e to the t here, then I get an expression for y that depends on t. So y equals negative 3/2 e to the t plus 11/2. If you take the time to eliminate the parameter, then you'll get the exact same rectangular equation here. And the sky's the limit. You know, whatever you want to drop in for x, just plug that expression in for x, and you get an expression for y. So x equals blank, then y equals -3/2 blank plus 11/2. So just fill in the blank there. That one works out particularly easy. You can verify by graphing this in a couple different ways. Graph it in rectangular form, that is, go back to functions, graph this, and then compare it to the graph of, say, one of these. You should see part of the same line. Now, it might not be all the same line. In fact, in the case of this one, you're not going to get all of the line because x is always going to have to be positive. E to the t can never be less than or even equal to 0. So it's going to kind of put a limit on it. You won't get the complete trace out of the line that you would if you chose that parameterization. Not that necessarily one's better than the other, they're just different. Let's take a look at problem number 44. We want the parametric equation of a circle with a center at -6 and 2 and a radius of 4. So center at -6 and 2 and a radius equal to 4. Well, that's going to look like this. It's going to look like x plus 6 squared plus y minus 2 squared equals 4 squared. That's just the generic form of the equation of a circle. But now I've got to parameterize it. Now I've got to write it in terms of x and y. So our experience with some of these problems, like problem number 22, is going to help us out here. I'm going to start by dividing both sides of this equation by 16, by 4 squared. So that's going to give me x plus 6 squared over 4 squared plus y minus 2 squared over 4 squared equals 1. And you remember working with these expressions before, where we had a couple things that when we added them, we had sine squared plus cosine squared is equal to 1. So that's giving us a kind of little insight into how we need to finish this one up. This is going to be my cosine term. So let me let cosine of theta equal to x plus 6 over 4 squared. What should I do with this term? Yeah, sine of theta equals y minus 2 over 4. You know what? I don't need the square there. Over 4. Because I'll get the square when I square both sides. Let's solve for x in this relationship. I'll get 4 cosine of theta equals x plus 6. Moving the 6 to the other side, I get 4 cosine of theta minus 6 equals x. And likewise over here, I get 4 sine of theta plus 2 is equal to y. So I kind of reverse engineered it. I came up with a couple of expressions that have x and y and the parameters theta. Let's take a quick look at the graph. So I got 4 cosine of t minus 6, and then 4 sine of t plus 2. So I don't think I need to go up to 4 pi again, or actually whatever that was. Let's just do 2 pi, zoom 0, followed by zoom fit. No, zoom square, sorry. Zoom 0 is zoom fit. So followed by zoom 5. Perfect. Circle centered at perfect timing. Centered at -6 and 2 with a radius of 4. Now, did you notice the orientation? If I made a subtle change to this, it'd still be the same equation, but if I made a subtle change, I think I can get this to trace out a different way. So if I type in a negative here, let's see, I'm hoping this will work. Oops. Negative t. It should give this graph a different orientation. There. So instead of tracing out counterclockwise, this time it traced out clockwise. So lots of different possibilities given different orientations. But let me finish things up with some homework. Try 1 through 25, 31, 41, and 43.